So in this video, we'll look at the meaning of this quantum number m sub L, which is the magnetic quantum number. So just to remind you, what we're trying to solve is Schrodinger's time-independent equation, and we want to do it in spherical coordinates. And remember, on the last one, we had that real big expression for the Laplacian of psi, and the whole purpose of doing this is because we're going to be looking at central potentials where U is only a function of R. It doesn't depend on theta or phi. And again, this was our XYZ to convert XYZ into R thetas and phis, spherical coordinates. Here's our little volume element in the two. And last time what we said is we broke up our psi into R, theta, and phi, and we plugged it in. That way it turned partials into total derivatives. Then we divided everything by this term. And then we multiplied by a factor such that the phi term didn't have any thetas or r's with it. And once we had that, and everything on the other side was thetas and phis and r's, sorry, just thetas and r's, we knew that this had to be a constant and that had to be a constant. And we set those two constants equal to m sub L squared. And when we solved just the phi part, we ended up with that. That's the azimuthal part, and it gave us a quantum number, m sub L, where m sub L could be 0, plus or minus 1, plus or minus 2, and so on. It looks like it could be all the integers. And we said these form an orthonormal system right here. Okay, so now on this one I wanted to say, what is this m sub L? So let me just go back into, if we go back to classical mechanics, we had something called angular momentum. Angular momentum. What was the definition? Well, for a solid object just spinning, it was I omega, but that was just a special case. In general, it's just R cross P. So there is the definition of angular momentum. Well, and again, if we wanted to take the cross product of this, remember R, you could have written it as x in the I plus y in the j plus z in the k. If we wrote it as a vector. And P, we could have written it as px in the I plus py in the j plus pz in the k. So if I really wanted to do the cross product of these two, if you remember how we did the cross product in classical mechanics, we just made a little 3 by 3 and we put this I, j, and k. And the next row was the three components of my R, which would, in this case, would just be x, y, and z. And the last one would be the components of P, which would just be px, py, and pz. Okay, so if I solve this, remember, found the determinant of it, this would give me the angular momentum in terms of the components of it right here. But suppose I just wanted to get the z component of angular momentum. The z component of angular momentum. So I only want the k parts right over here. So really, I guess if you're finding the determinant, it would just be this times this minus that times that. So it would just be x py minus ypx. Remember, you just go down this way and come back. Minus ypx. Now, suppose I wanted to find out what was the, if I turned this into an operator, what is the LZ operator? Now, what are we talking about? We're talking about the angular momentum of the electron orbiting the atom. We're talking about the orbital angular momentum. Remember, we already did the spin angular momentum when we were doing our ups and downs. When we had S sub z operator, that was just the spin of the electron. That wasn't the orbital motion. Right now, we're just looking at the orbital motion of it. So if I make this an operator, all of these just have to become operators. That's just x operator, py operator, minus y operator, px operator. Or if I plug in what the operators are, we know x operator is just x. Py is that minus I h bar partial with respect to y. Minus y is just y. Px is I minus I h bar partial with respect to x. Okay, and so now I can pull out let me pull out the minus I h bar. So LZ operator is just minus I h bar, and it would be x partial with respect to y minus y partial with respect to x. So that looks like the orbital angular momentum, but I'd rather not keep it in terms of x's and y's. Why? Because we're in spherical coordinates. I'd like to put that in terms of thetas, r's, and phi's. Well, if I were to say, let's just look at this. Suppose I had to say, what is the partial with respect to phi? Now phi, there's no phi in this, so phi is only in the x and y. Phi is just a function of x and y, and if I wanted to find out what it was, that would be, just using the chain rule, it'd be the partial with respect to x, partial x with respect to phi, plus the partial with respect to y, partial y with respect to phi. Okay, since phi is only a function of x and y, you don't have to do the z. Okay, well, let's plug in what the partial of x is with respect to phi. Partial of x with respect to phi. We know what x is as a function of phi. It's right here. If I take the derivative of this with the partial with respect to phi, this doesn't do anything to this, and it just takes the derivative of cosine of phi, which is minus sine phi. So it becomes minus r sine theta sine phi. So this just becomes minus r sine theta sine phi. But y is r sine theta sine phi, so it must just be minus y then. So this is just minus y. So that's what this term is right there. What is the partial of y with respect to phi? So now we're just going to come over to here and take the derivative of this with respect to phi. Well, it doesn't do anything to this. It turns the sine of phi into cosine phi. So it's just r sine theta cosine phi. R sine theta cosine phi. But we can see that r sine theta cos phi is just x. So I can just call that x. So I can put that goes up into here, this right there. So let me just rewrite this again. Partial with respect to phi is equal to partial with respect to x times, what is that, minus y, because that's what this is, it's minus y, plus partial with respect to y times, whoops, that was this term right here, partial y with respect to y is x times x. Now, I can bring this y out in front and this x out in front right here, because there's no, you're not doing anything with x with y right there. So partial with respect to phi is equal to, let me put this term first since it's positive, x partial with respect to y minus y partial with respect to x. Well, that looks familiar. That's what I have right here. That is that right there. So it looks like the z component of the orbital angular momentum operator, L sub z operator, is equal to minus I h bar times this difference, which is just partial with respect to phi. So that right there is our angular momentum, the z component operator of the angular momentum. Okay, again, we have two angular momentums. We had the spin before, but that's different. That was a spinning. This is the orbital right here. Okay, so now that we have an operator, what if we operate this thing on my psi? What if we operate, remember, if we operate this on our wave function, we should get what? The value, what you'd read from the z component of the angular momentum, lambda, times your psi again. And these would be my eigenvalues, and these is what I should be able to measure from it. Well, let's see what that gives me. If we plug in L sub z, psi, well, we might as well write psi as r, theta, and phi. R sub r, theta sub theta, phi sub phi, equals lambda, that's what we want, times my psi again. R sub r, theta sub theta, phi sub phi. Okay, we're just plugging in this right here. Okay, well, let's plug in, now we can plug in that down into here. So we get minus I h bar partial with respect to phi times all this, r sub r, theta sub theta, phi sub phi, equals, this stays the same, lambda r sub r, theta sub theta, phi sub phi. Okay. Well, from this, I can pull out these two terms out in front because this is only a derivative with respect to phi. So we get minus I h bar, and I can pull out the r sub r. I can pull out the theta sub theta. And all I have to do is just take the derivative with respect to phi of d phi, and this becomes a total derivative too, because there's only phi's in there. So we can make that a total derivative. d phi of the total. Okay, so there's the left side. I just pulled out the other parts. And then we have on this side, we still have lambda r sub r, theta sub theta, phi sub phi. Okay, both sides have an r and a theta, so I can cancel them out. So they just kind of pass through because this only depended on the phi part of it. So these two terms I can just cancel out because they're on both sides. Okay, so now what am I left with? I'm left with minus I h bar, the derivative of big phi, d phi, equals lambda big phi. Okay, we might as well plug in what big phi is. We know what it is. It's right there. What's the derivative of that with respect to phi? So we end up with minus I h bar. If we take the derivative of this with respect to phi, I still get the 1 over the square root of 2 pi take the derivative of this with respect to phi, I still get an e to the I m sub l phi times, and then what comes down in I m sub l and that equals lambda times my phi, which is this again, 1 over the square root of 2 pi e to the I m sub l phi. Remember, what we're trying to find is lambda, because that's my eigenvalues. Well, what can I cancel? Well, they both have a 1 over the square root of 2 pi. They both have an e to the I m sub l phi's. And so I got my lambda. Lambda. These are the possible values of the z component of the orbital angular momentum. The possible values are, well, I have a minus I times an I. That just gives me 1. And I get an m sub l h bar. So this is m sub l h bar. So that must be the values of L sub z. So this is what, so L sub z, the z component of the orbital angular momentum of the electron, we could say, is m sub l h bar, where m sub l is equal to 0 plus minus 1 plus minus 2, dot, 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 dot. So that's what the m sub l is. It's the z component. If we go back to what Bohr said, remember what Bohr said. He said the total angular momentum, total, was equal to nh bar, where n is equal to 1, 2, dot, 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 dot. Little different right here. First of all, he said angular momentum couldn't be 0. Well, here, the z component can be 0, plus or minus h bar, because it could be plus or minus 2h bar, plus or minus 3h bar. So he didn't quite get it right. It wasn't that the total angular momentum is nh bar, is that the z component is 0 plus or minus h bar plus or minus 2h bar and so on. Right there. Okay. So we've got the z component of angular momentum. So now if we were to go back and look at the Lx and Ly, they would not work out simple like this right here. We're never going to be able to know exactly what the angular momentum is of a vector right here. I mean, if you knew, let's just say here I have a bicycle tire here. We can look at the angular momentum. You'll notice right here, if I were to just look at this right here, spin this, we could say, well, it has a z component of angular momentum like that, but the atom could never be like this. The reason why is, you notice, you're on a plane right here. This orbital motion is in a plane. Well, how well do you know this component of space? Well, you would know it really well, because you know it's between almost exactly. Plus, it has no momentum in that direction, and so it would violate the uncertainty principle. That is, you can't have just something spinning like this, because it would violate the uncertainty principle this way, because there's no momentum this way, and you'd know the position really well because you're in a plane. So this can never happen right here, and we'll see later that what happens to this thing right here. This thing likes to what? Precess like that. You notice when this thing precesses, it kind of goes around. Actually, I shouldn't do it while it's spinning. When this thing precesses, I do not know. You notice you're never in a plane, but the z component always stays fixed. You notice the z component is always staying fixed because this angle is staying fixed. And that's what we'll see what happens in this orbital motion of the electron. It can't just be like this, because it would violate the uncertainty principle. But if it precesses like this constantly, then the z part of it stays fixed, and the total angular momentum stays fixed. And those are the two things that'll stay fixed right here. But we're only on the z component right now. And so next time we'll pick up and we'll try to solve this equation right here. And hopefully we can separate out the r's and the thetas to break it into two smaller equations and then try to deal with those separately. Okay.